this is Physics 1C for March 2nd. Today we're going to be talking about electric flux and Gauss's law. And yeah, we're just going to kind of keep going with this concept of the electric field that we've learned about and look at basically just another formulation that gives you a lot of the same results from previous chapters, but is ultimately more powerful as a way of finding electric fields, or possibly as a way of finding things like charge densities. So the first thing to talk about is electric flux. So electric flux is directly related to electric fields and kind of the way they flow, you might say. And the way we think about it is this. If you have, in some region of space, if you have some electric field lines, so let's say we've got an electric field, and we'll choose to start with just a really simple one. So we have an electric field that has lines that point like this, for example, just kind of straight, uniform electric field. So those are your field lines, like this. And just ask you to like kind of, well, I guess what I could do, we could make it somewhat three-dimensional if we do something like this, I guess. I don't know how good this is going to look. Let's see. Okay, so imagine that it's an electric field that's uniform, and it points to the right, and it kind of, you know, it comes out of the page, into the page, but it's just everywhere it points to the right. Just a uniform, nice uniform electric field. In order to define what flux is, what we need to place like a square or some kind of a surface inside of this. And so the first thing I'm going to do is, let's say that we take a surface. We'll do it right over here. Let's not use that color. I better actually use lines, otherwise it'll look bad. So let's say we have a surface. So our surface is going to be given. Click on you. There we go. Copy paste. So let's say our surface looks something like this. It's going to be just a flat plane that is oriented like this. Okay, so we've got a plane like that. And let's say that it has an area that we call A. So A represents the area. If our plane is perpendicular to the electric field lines, okay, so like the surface of the plane, if at every point the electric field cuts it at right angles, then we can define electric flux like this. So the symbol that we use is a capital Greek letter phi, which I really don't like this symbol because it's a little bit unwieldy to draw. Regardless, we use phi with a little e for a subscript. This is what flux is. In this case, it would be really simple. It would literally just be the size of the electric field multiplied by the area. And from this, you can tell what the units would be. The units are going to be, the units for electric field are newtons. You divide by coulombs, and then the units for area are meters squared. Electric flux is a scalar, not a vector. Now, the fact that it's a scalar should tell you almost immediately. I mean, if you know much about how vectors work. Oh, my camera's not on, is it? Sorry. So, if you know much about vectors, and I tell you that this thing is a scalar, then that should tell you something about how this calculation has to be done. So I'm giving you the most simple possible example, just where the size of the electric field multiplied by the area gives you the flux, right? But the fact that flux itself is going to be a scalar quantity, what does that tell you about how this multiplication has to be done? Like, how do we do the multiplication? And I'm going to kind of go back to some things that you probably learned in Physics 1A. So in Physics 1A, you learn how to multiply 3 different things involving vectors, right? So let's just go through a little brief review right here. If we're talking specifically about multiplication, there are 3 ways you can do it, okay? One way is a vector times a scalar. Right? And And an example of that would be Newton's first law, or second law, sorry. Net force is equal to mass times acceleration. Mass is a scalar, right? Acceleration is a vector. And we know how to multiply a scalar times a vector. When you multiply a scalar times a vector, it basically it scales up the size of the vector, right? So if the mass was 3, you get 3 times the acceleration. But if the mass was 6, you get 6 times the acceleration, and the net force would be double, right? What are the other ways that you can multiply objects that include vectors? Now, obviously, we can do scalar times scalar, but that's not very interesting, right? 3 times 2 is 6. That's just normal multiplication, right? But what about...
Dot product?
The dot product is one possibility, right? So if you do a vector, and then you do dot product with another vector, I really should put some symbols over this or something like that, then this one is the one where, what's an example of this one? Work, right? Work, which is a scalar, is equal to the vector of the force dot product with displacement, right? And that takes two vectors, you multiply them by each other, and you get a scalar, right? And finally, the third option would be vector cross product, right, with another vector. And an example of that would be like torque, right? So torque, which is a vector, is equal to this cross product of r cross f, right? So in all of these cases, what do you get? So in the first place, when you do a vector times a scalar, what is the answer? Is it a vector or a scalar?
Vector.
It's a vector, right? And if you do vector dot product with vector, what do you get as your answer?
Scalar.
And if you do vector cross vector, you get vector, right? Okay. So let's come back to flux. So if I tell you that electric flux is a scalar, which of these 3 possibilities does the multiplication have to be?
The second one.
Second one. This is the only possibility, right? So that means that there must be a more general expression involving the flux that involves a vector dot product with a vector. That also means somehow that the area vector, sorry, I just kind of jumped to the end. The area must have a way to describe it as a vector, right? So let's write the more general version of this. And in order to do this, what I'm going to want to do, how well does this work? Can I make a... Yeah, it's not going to work very well. So let's think about how this would work. So flux is equal to E times A in this case. And what I would say is that this is the maximum amount of flux you can get. Okay. Now, what flux itself is involves basically kind of like the number of electric field lines that actually penetrate through your area. So if you wanted to get the minimum possible flux, what you could do is you can take your paper or your plane right here, and you can orient it so that instead of being perpendicular to the field lines, it's parallel to the field lines, right? So if I took a plane, and if I take or even the same plane, and I rotate it so that it's now oriented like this, so now that it's like sideways, basically. So we go, let me do another shapes line. Just go boom, like copy paste, like that. Then let's give these different names here. So we'll call that one A1, and we'll call this one A2. All right, so different areas. And we'll come back here and we'll just call this electric flux. We don't need to change that definition, right? So if I want to know what the flux through surface 2 is, then I'm going to say that in this case, all the field lines are parallel to the surface, so none of them actually puncture the surface, right? None of them actually go through it. So the flux through that surface is going to be E times A. And now we need to multiply by something that automatically makes it 0. But we know that it's going to have to involve a dot product. We know for a fact that you have to use a dot product to do this, because we know the answer is a scalar, and electric field's a vector. So there's a problem here, right? So in order to make that work, what we do is we say, well, it must be the case that if the electric field's a vector, maybe we can make a vector out of our area somehow, and then do a dot product so that we would define E times A2 times the cosine of some angle, theta, to be what our flux is, right? Now, in order to make it so that this flux is guaranteed to be 0, there's an easy way to do it, right? What does theta need to be in order for the flux to become 0?
90.
90, right? Or 180 or whatever. So if we know that theta is 90, then we also know something about how to draw our area vector, right? So I guess in general we could have had multiple possibilities. I guess one possibility is we could have made our area vector go from like one corner to the other corner. That could have been the direction of the vector, right? Or we could have made the area vector just point along one of the sides like this, right? But now we actually know exactly what it has to be. In order for it to make a 90-degree angle with the electric fields, the area vector has to point perpendicular to the surface, right? That has to be the direction of your area vector. So in this case, A1, the area vector points perpendicular like this, and in the case of A2, it points up like this. It could, in both cases, either point up or down, okay? But we'll see how we define that later on. But for now, just, basically the area vector is going to point perpendicular to your surface. If you do that, then the angle made between this area vector and the electric field lines is a 90-degree angle, and it satisfies what we just wrote down here, okay? So that means that this is how we're going to define flux. So in general, flux is going to be defined, phi sub E, by just taking the electric field and dot producting it with the area vector, like that. And that's what flux is. I'll give you an analogy to help you understand more about this and why we define it this way and stuff, but I'll just stop right there now that we've introduced it. Does anyone have any questions? I don't usually explain it like this, but we're talking about this stuff in Physics 1A, so it just seemed reasonable. So the next thing to do then is to give you some kind of analogy as to why this should matter, or why do we care about flux? Like, what's the point? What's the point of doing, electric field times area? Who cares? So I'm going to give you an example of why this might matter. So what I think the best analogy is to use is like solar panels. So if you have a home, okay, and to keep things really simple, our home is going to be basically like a cube, so that the top of the house is going to be completely flat, okay? So we've got a door, maybe some windows, and on top of the house, the entire roof of the house is going to be covered in solar panels. Okay, so the entire roof of the house just has solar panels on top of it. And again, the top of the house is flat. So now we have to add in here the sun. Let's get another color. So let's say, for example, that the sun is directly overhead, like it's up here at noon. Now the sun is so far away, actually I should probably put it farther away on this picture. Okay, let's come over here. Let's get a little more room. Try not to block it with the chat window. So the sun's so far away that the rays from the sun, when they hit the earth, they're all basically parallel, right? So the light coming from the sun kind of comes down and it goes like this, right? It basically is like just parallel rays coming, because the sun is so far away, they basically are parallel rays that all come in like this, right? And when they hit the surface of the solar panels, when the sun is at its maximum point in the sky, the solar panels are at their most efficient, right? They're getting the absolute maximum power output because the sun, all of its rays are basically shining directly down on these solar panels, right? So you can think of it as like the solar flux, right, is at maximum at this point. This would be maximum solar flux. But if we consider an earlier point in the day, and we'll just use red, then when the sun is just rising, and it's maybe down here in the sky, now the the rays from the sun are going to be coming in like this, right? And so you'll get 0 solar flux. The solar panels aren't going to do anything at this point, right? And then as the sun is at an intermediary point, like if the sun is like, let's say right here, let's use a different color, then you're going to get something in between, right? Now, will it be half as much? Not really. It turns out that it's going to be related to the cosine of the angle made between these rays and the surface of the solar panels right here, right? So, just like the way that flux is calculated using a dot product, the amount of energy that's coming to these solar panels is also going to be calculated using some kind of a dot product. Meaning when the angles are coming in at 45 degrees, you're going to multiply by cosine 45, and at that time, the solar flux is going to be about, well, cosine 45 is equal to what? It's like 0.707 or something, right? So this would be something like 71% solar flux or something like that, if you were at that angle like that, right there. Anyway, so that's electric flux, and we're going to use this for Gauss's law, but it is also going to have a lot of implications later on in the class as well, when we start talking about magnetism. So, does that all make sense? As to like how we define it? We'll do some examples, of course. But does anyone have any questions? Does that all make sense?
Looks good to me.
All right, so let's look at right, this one right here. So I just wrote this other thing down here as I was waiting. Flux can be 0, it can be positive, and it can be negative. So in that sense, it's kind of similar to work, right? The work done on an object by a force can either be positive, negative, or 0, right? Friction tends to do negative work, but for a falling object, gravity does positive work, right? So flux is the same thing, and we'll look at how that can work out. So let's look at the flux through a cube. So we're going to use a similar electric field to what we used up here. In fact, I'll just redraw it. So we'll start off with an XYZ coordinate system like this. All right. And within this coordinate system, we're going to put a cube. And we'll just put the cube with its edge over here. So let's draw some squares. So we'll have one square out here in the front. Make that one darker. We'll copy this one, paste it, put it back here, like that. Let's make it a little bit closer. And then we're just going to connect all the sides. Like this. Should be the same length for all of them. So this is going to be a surface. In this case, it's a closed surface. And within this region, we're going to say that this is the positive x direction. And we're going to say that we have an electric field. Let's go back up to the problem. So the electric field is oriented in the x direction in empty space. So we're going to say that our electric field looks like this. It's equal to some value that I'm just going to call E multiplied by I hat. Okay. So that means that our electric field lines basically permeate this entire region. They go through the cube. So they look like this. Oops. Make them green or something. So we basically have electric field lines running through this space that look like that. And I don't know if this is super obvious, but when I say that the electric field is E times I hat, that doesn't just mean it's in the XY plane. It's also in the Z plane, right? Basically, everywhere throughout space, you can just imagine that there's parallel lines going, well, just everywhere, basically. And they pass through this cube, okay? And the cube has an edge length L. It's placed in the field and oriented as shown. We want to find the net electric flux through the surface of the cube. So the length of each of these sides is L. So this is L. That's L. L, L, L. So then this side's L2. And yeah, we want to find the flux through the cube. So I'm going to come over here to, let's use a different color, we'll use red or something. The left edge of the cube over here. Do we want to label the sides? We probably do. We'll call this one 1. No, that's too confusing. We'll just call this the back, or the left. We'll call this the left side. Okay, so if I have a uniform electric field that's flowing through my cube, what's the flux through the left side going to be?
Should be 0.
It'll be maximum.
So on the left-hand side, we're going to have to take the value of our electric field, which is this, and dot product it with the area vector associated with this left side right here. So I'm going to go ahead in here, and I'm going to draw that area vector. We're going to say that that area vector points directly to the right, like this. That's going to be our area vector on that side. Okay, so it's going to be parallel to the field lines, which means that when we do this calculation, we're going to get the electric field, which is E, times the area, which is, it's a cube, right? So the area of a face is going to be L squared. And then the angle between the two of them is going to be the cosine of 0. So we end up just getting E times L squared for the left-hand face. Oh no, I'm so sorry to be so confusing. I did something wrong. Just want to erase that. You know, we don't really need the XY coordinates anymore, do we? Yeah, we don't really need those anymore. So I forgot to say something else. When you have a closed surface, the area vectors are always going to point out away from the surface, okay? So on the left-hand side over here, the direction of the area vector is actually going to be back this way. Like that. So the rule is if you have a closed surface like this, the direction of the area vector is going to go out away from the surface. Like that. And we can kind of go through and put our area vectors on each surface. Maybe we should do that so that it'll be really clear what we're doing here. So on the right-hand surface, it's going to point out away this way. You guys tell me, what direction is the area vector on the top surface going to point?
Upwards.
Up, yep. What about the bottom surface?
Downwards.
Yep. And then the front surface should be this way, like positive Z, you might say, right? And then the back surface
away,
be negative Z, like that, right? Okay. So those are all of our area vectors. We'll just label them as such. I guess I could also say that this is going to be front. This is going to be bottom. This is going to be top. This will be back. This will be right. Okay. So let's go back and fix this. What did I do wrong on this first step right here for the left-hand side? Yeah,
the angle.
Right. Yeah. So now the angle should be cosine 180. Let's erase all this. So we'll get negative EL squared now. Here we go. Okay, let's go through the rest of them. So there's 5 more. So on the right-hand side, right, we've got same kind of idea, E dot A. We're just going to use the right vector. And for this one, we'll get just, yeah, EL squared, that's right. Cos 0, and that's just going to be positive EL squared. What do we want to do next? Let's do the top. For the top, it's going to be... What's the answer going to be for the top one?
0.
Yep, because now the angle between the electric fields and our area vector is a right angle, so we do cosine of 90, and we get 0. Same thing for the bottom, right?
And the front and the back.
And the front and the back, right? So do you all want me to write down the front and the back, or can everyone see that now?
I'm good.
This is a right angle between the area vector and the electric field coming out the front. And on the back, this is also a right angle. So same thing. Those are also equal to 0. So the flux through the front is equal to 0, which is also the same as the flux through the back. Right? Okay, that's all very simple. I'm going to show you a harder version of this problem as soon as we finish it, because you're going to see something on your homework that's just like this with a couple changes. So the final thing we want to do is we want to find the net electric flux. And yeah, Delvino, that's right. The total flux would be 0, exactly. So if we add up all of our fluxes here, say like sum all the flux, but that's not usually how we write it. We usually just write it as like the net flux, or the total flux, however you want to write it, would be the sum of all of these. We'd have to add them all up together. So ultimately, we'd be doing negative EL squared for the left side, plus EL squared for the right side, plus 0, plus 0, plus 0, plus 0, right? So we end up getting total of 0. Now what you'll see as we continue to do this is that once we've learned Gauss's law, you would have been able to answer that part immediately. You would have known. Gauss's law is going to tell us that the answer would have had to have been 0. The net flux through a closed surface is going to be 0 unless there's something inside of it. There has to be some kind of a charge inside of it to get a flux, as we'll see here in a second. Okay. Yeah. So how could this problem be a little harder? So the version of the problem that you have in your homework looks something like this. So we change the definition of the electric field. Okay. So let's think about it like this. So what if the electric field had been given as, okay, let's see if I can think of something off the top of my head that's going to be similar. So remember that this was the origin, right? I don't really want to draw the axes on there again, because it's just going to clutter the diagram with a bunch of other dark lines that are going to make it hard to distinguish what's going on. So what if the electric field vector, instead of just being uniform throughout the region, what if it was given by something like, let's say 5x multiplied by I hat plus 0j hat plus, let's say 3z times k hat. I think this is almost exactly what your homework problem is like. Just that the, what do you call it? The coefficients of your ij's and k's will be a little different on your homework. So what if that was what the electric field was? Now I can't draw this electric field. It's been a long time since I did any kind of 3D graphing. I don't really know what this function would look like. So our electric field lines are meaningless now, okay? So I'm going to leave them on there, okay? But just remember that these field lines are no longer the same thing as this electric field. Everyone's okay with that, right? Is that, I should actually first ask, is that obvious? Is it obvious that the electric field lines that I've drawn here are different from this one? It's probably not obvious.
Yeah.
Or maybe obvious to some people, but not to others. This field has a component that points in the k direction, right? So if I came out to the point, let's say like 1, 1, for example, right? So say I came out to the point 1, 1. No. Let's do this. Let's come out to the point L, L, L. Okay? So if we're at this is your x, y, z's. Okay? if we're at that point and I want to know what my electric field is, right, it would be equal to 5L I hat, right, plus 3L times K hat, right? Which means it's going to have a component that points to the right, just like this one here. But in addition to that, at the point LLL, which is here, it's also going to have a component that comes out into the z direction, right? And let's see, so it would be like 5I would go this way, right? Let's call that 5L times whatever. And then our z-coordinate has to be kind of coming out this way, so that's going to be 3L this way. So our electric field vector at this point would point like this. That would be the direction of our electric field, right? So immediately, just by picking one point, you can see that it no longer has this nature that it's uniform like this anymore. Does that make more sense, Prince Ali? In order to actually draw out this electric field, we would need to use, well, if you have like I think TI-89s can do this. They can draw vector fields. Can you put these into Wolfram Alpha? Will Wolfram Alpha draw vector fields for you? It probably does, right?
Man, let me see.
Yeah, why don't you guys try it? Okay, regardless, let's talk about how we would solve it now. I think it does. I think it almost has to, because it can do almost anything. So what if this was our field, okay, and now we want to calculate the electric field. There was an app that you used for 220 for vector fields and whatnot. Okay. If you know what the name is, maybe we could pull it up. So what would the flux through this one be? What would the flux through the left side be now? So we use the same definition. We're just doing E dot product with the area vector, right? And that's going to end up being the value of E times the left area vector here. Now what I would say, I don't know if this is going to make it simpler. We're doing left here, right? That the left vector, the left area vector, is basically equal to L squared multiplied by what unit vector should I put in here for the left unit vector? The area left side over here. What's the direction of that vector?
I.
Is it I?
Or negative
Negative I.
It's negative I, yeah. Oh, you guys are so quiet today. I must have my volume turned way down. I apologize. I'm going to fix this real quick. Oh, yeah, it's way down. There we go. Okay, so let's just do the actual calculation. So on the left-hand surface, we would write down the entire electric field right here. So 5x I hat plus 3z k hat dot product with L squared times negative I hat, right? What do you get when you do k hat dot k hat? Sorry, k hat dot I hat.
J hat.
J dot. They're orthogonal.
That's not right.
It should be
What's the angle between k and I?
90.
So when you do dot...
So it's 0.
So it's 0, yeah, exactly.
0.
And if you do I hat dot j hat, you get 0. If you do k hat dot j hat, you get 0. You only get something if you do I hat dot I hat, basically, right? So this is going to end up being equal to 5x. I hat dot negative I hat just gives you negative 1. Excuse me. Times L squared, right? Okay. But we also have an x in here. And we're looking at the left surface. All across the left surface over here, what's the value of the x-coordinate? Remember the bottom,
0.
It's 0, right? All along this plane, this is a YZ plane, right? The y goes up, the z comes out. So all across this entire left-hand surface, the x-coordinate is equal to 0. Now, I know it's very difficult to, like, see things three-dimensionally, and so this requires a lot of imagination on your part. I think for a lot of people, this is part of what makes Physics 1C hard. So make sure that you can see this, that x is equal to 0 in the left-hand face. So that's the answer.
Looks like Wolfram only does 2D plots.
Okay. Well, this is technically a two-dimensional field, right? It's just x and z. So you could plot it, and then it would just repeat itself in the y direction, right? Okay, so the flux through the left-hand side is 0. Can everyone see that, based on what we just did? All right. So what about the flux through the left-hand side? Or the right-hand side, sorry. So the flux through the right surface. To do this, we're going to need to know what the area vector for the right-hand surface is. What would it be? We know it's the area, which is L squared.
L squared I hat.
Yeah, positive I hat now, right? So the flux through the right-hand surface is going to be, again, E dot with that vector. Literally the only difference between the right and the left is that one's positive and one's negative I hat. So the answer is just going to be different by, well, it's just going to be 5x times L squared. But
It's different by sign.
what is, yeah, the sign's different, right? But what is the value of the x coordinate? Let's go back to our
L.
picture. It's L, right? Because the side length is L, so when we come over to a position right here on this corner, that corner has a coordinate of what? 0, or be L comma 0 comma 0, right? So all across the right-hand surface, it has the same x coordinate, right? And because it all has the same x coordinate, then x is equal to L, and the flux through the right-hand surface would be equal to 5L cubed, right? Now, I left out what these units need to be right here. We're just not going to worry about that for now, okay? But does that make sense to everyone?
Mm-hmm.
So now you might be able to see a difference in what we did before. So in the previous problem, the flux through the right side was positive EL squared, and the flux through the left side was negative EL squared. And as a result, when we summed those two, we got a total of net 0. That was the first problem that we did, right? But now, that's not true anymore because the flux through the left is 0 and the flux through the right is not 0. So we now have some kind of net flux flowing through our cube, right? Okay, x is equal to L because our cube is situated so that the left, I don't know what you call that, the left back corner right here is at 0, 0, 0. That's the origin back there, right? So if you go in the x direction, positive L, you're going to end up at the other corner right here because the cube is L by L by L, right, Delvino? Does that make sense? So that point has to be... So in fact, what we could do is we could say, I'll ask you guys this question. What would the coordinate of the top right be? What's the coordinate of this one right here? We can go one at a time. What's the x coordinate? Kyle got it.
L.
That's right. It's L, 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 right? This is L, L, L right here, right? The one back here would be something like L, L, 0, and so on and so forth. You should be able to go to each of these cube faces and figure out what the coordinate is, right? Okay. Now we can continue with this problem. I don't know if you want to or not. Two of them are going to be really simple, actually. Can anyone tell me which two other surfaces are guaranteed to be 0 for our flux?
The ones with the A with the in the j hat direction, is that the front and the back?
J hat direction would be anything that has a positive j hat as or negative j hat as its unit vector, right?
Yeah.
So what would those be?
Are those the is it the front and back in this coordinate system? Or is it the top and the bottom?
Yeah, I can see why that's confusing. I apologize. This is our coordinate system that I'm using. X is right, Y is up, Z is this way.
So then it would be top and bottom.
Yeah, okay. So we know that the flux through the top and the bottom is 0 because there's a 0 here, which means when you do the dot product, you're going to have like an I dot J, you're going to have a K dot J, and those aren't going to give you anything because those are 0. So that means the flux through, what is it, top is equal to the flux through the bottom is equal to 0. Now the other ones will have some answer, but I will also say the flux through the back is also going to be 0 for the same reason that this one was 0, because the z coordinate on the back side is 0, right?
Mm-hmm.
So we're only left with the flux to the front. So for the flux through the front, we're going to get that whole thing. Dot product with the area vector for the front, which I would say is going to be L squared multiplied by positive k hat, because again, k is coming out of the screen. Right? This is the k hat direction, the z direction. And the z coordinate at this point, what's that equal to?
L.
L, right? So we end up getting 3L cubed is equal to the flux through the front. And now if we want to find net flux, we'll just put it right here so we can keep everything on the same kind of area. The net flux would end up being equal to that plus that, because every other face was 0. So you end up getting 8L cubed. That's a problem that I have on your homework that everyone always gets really confused with. And I just want to emphasize that you can solve this problem by just using the definition of your... you got to know the definition of the dot product. You need to know how to write your IJKs, your unit vectors. But that's it. I say that because top and bottom are also 0, Kyle. Whoops. You want me to explain again why the top and bottom are 0 here?
Oh no, that was from earlier when you asked
Oh, gotcha.
which
Gotcha.
ones
Gotcha.
are 0.
Yeah, for sure. So we're going to learn more. What's up? Go ahead.
Could you actually explain that one more time?
Yeah, sure. So let's actually go into more detail about what happens with the top and the bottom. So the flux... The flux through the top would be equal to 5x I hat plus 3z k hat. That's our electric field, right? We dot product that with the area vector associated with the top. And the area vector for the top should be the area, which is L squared, multiplied by positive j hat, because the area vector on the top points upwards, which is the positive y direction. Right? So when I do this dot product, I end up getting an I dot j, which is 0, a k dot j, which is 0, so you just have 0. Because the electric field has no vector that points in the positive y or negative y directions, there's no flux. It's just like... Okay, did that answer your question?
Yeah, that made sense.
It's literally just like this situation, right? Yeah. 0 flux. Okay. Yeah. Okay, again, you got a problem like this, just keep in mind when you're doing it that it's based on just the definition of flux, because what we're going to learn next is that in order to do the flux over a curvy surface, you're going to need to use integrals. And your temptation when you do your homework is going to be to do integrals with this. I've noticed in the past that it ends up wasting a lot of students' time as they struggle to solve this type of a problem. But really, it's not super hard. It's just kind of time-consuming. It's not that time-consuming because there's actually only 2 things that had answers, right? This one and this one. Everything else was 0. So, yeah. All right. So, let's talk about the relationship between flux, field lines, and charges now. Okay. Now, with the first 2 examples we talked about, we used uniform electric fields. This one and this one. And then I made it a little more complicated by using an electric field that was dependent on x and z, so no longer uniform, right? But what we've seen in this class is the type of electric fields that we get, they don't always look like that, right? If I have, for example, a positive charge, if we think back to, hopefully you remember what we learned last week, the electric field lines for the positive charge kind of go like this, right? They point out away from the positive charge, radially, and the field lines, they tend to be somewhat symmetric. Well, they are symmetric, they're radially symmetric, they're spherically symmetric, and you get field lines like this, okay? Now, we also know what the value of the electric field produced by this charge is, right? It's basically equal to k times whatever the charge is q, so we'll just say this has a charge q, times r hat, and then you divide by r squared. That's what the field looks like. This field is quite a bit more complicated than the field we looked at in the previous problem, because it has this r hat here, and it's got this radial dependence, right? So for example, if I was to come over here and say, suppose we take a flat surface, right? And I ask you what the size of the electric field, or sorry, what the flux through some flat surface is here, it gets kind of complicated, right? If it's not super obvious, let me show you why it gets kind of complicated. So for our area vector, at the top, the area vector goes this way, right? At the bottom, the area vector goes this way. And only in the middle do you get a nice simple relationship for what direction the area is related to the electric field, right? So it's just this one that's kind of got an angle of 0 between the two. But the other two have some other angle. And whatever that angle is, it's not necessarily going to be the same up here and here, right? So can you see that in this case, calculating the flux is a little more tricky?
Mm-hmm.
Okay. Now, we could have chosen a surface such that calculating the flux wouldn't be so tricky, right? Like,
True.
what we could have chosen is we could have taken our, and now for this I'll make things like a little more symmetrical. So we'll start off with a point charge. Like here, Q. We'll make it positive. And then we'll draw our field lines. I'll try to make them straight. So we'll have like one right there. I'll make them all the same size too. Copy, paste. 4, 5, 6, 7, 8. I think I made one too many. Okay. And we'll just have all of these stick out away from this object. So one of them will go, oh no, I can't. There we go. Yeah, one of them will go this way. One will go down. One will go to the left. One will be like a 45-degree angle. And these lines, they extend out forever, so even if I stop them a little short, they're still going to keep going. And I could make them a little bit longer. Okay, so that's what our field lines look like, right? So what kind of surface could I draw around my charge so that we don't get this awkward situation over here where we get changing directions of the area vector? What if I wanted to make it so that my area vector was always exactly perpendicular to every one of these lines? What kind of surface could I draw around my object?
Sphere?
A sphere, yeah.
Exactly perpendicular?
Yeah, we want the surface to always be perpendicular to the field lines. Okay. So he's right. If we choose a sphere... What's up?
It's okay. I understand. I get it.
Okay. So we put a surface around like that, and I tell you that it's a sphere, so we need to draw in here like something to make it look kind of spherical, like this. So we've got a sphere that we draw around this, right? And now we look at the direction of our area vector on all the surfaces where the black lines are electric field lines. So now, at this point, the direction of the area vector is going to point like this, right? But it gets kind of weird because, before we were talking about flat surfaces. So in order to really define what this area vector is right here, what we do is we kind of break up our entire surface of our sphere into, like, you can imagine, like, gridding it off into a bunch of little tiny pieces, right? And saying that each one of those little pieces that we cut out right here is going to have an area vector that we call dA, okay? So the area vector at the top right here will point this way. The area vector over here would point this way. Sounds like someone's dog's coming to say hi. Area vector over here is this way. And now at every single point, the angle between the electric field and the area vector is 0, right? At every single point, right? And let's also indicate on here that the radius of our sphere is r, okay? Now, if we do that, what we can find is we can actually calculate the total flux through the surface in a pretty simple way. But we can't really do it in the same way we did before. And so now what we have to do is we have to come up with a definition of a flux through a curved surface, okay? To find the flux through a curved surface, we need to basically break the surface up into a bunch of tiny little area elements and then do a surface integral. Like this. And this is going to be done over a surface. Okay. Now, if it's a closed surface, we're going to draw a little circle around here. And what that means is that you do the integral over the entire surface, basically. Okay. Now, I'm going to tell you right now that in this class, I don't think, but there may be one or two, but almost every single problem that you're going to do where you have to do a calculation like this, you're going to find a way to avoid doing the integral. And I'll show you exactly how that's going to happen here. So what we'll do then is we'll say that our flux is equal to... Now we've specifically made it so that the electric field and dA point in the same direction, right? So what that means is that our E dot dA, which starts off as a vector, we can just write that as E times dA, right? Because the angle at every single point is 0, whether we're on the front of the surface or the back of the surface or any point on the surface we choose. This is always true, right? So that our surface integral just becomes... I'm not always going to write these as double integrals, by the way. And I know that's probably not something that will make a lot of you happy, but it's the nature of like how this is written in the textbook and stuff like that. But I'll try to remember to write double integrals every time. So now our thing looks like this. But here's the part that's really helpful, and this will happen in virtually every problem that you do with this. How does the electric field over here compare to the electric field over here? Assuming that our sphere is actually situated, and let's do another place where we can actually see it. How does the electric field at this point compare to the electric field at this point?
Constant in magnitude.
They should be the same, right? Because the electric field depends on K, which is a constant, Q, which is just the charge, which it should be a constant, and then it depends on R, right? It depends on R. So at every point along this surface, the electric field is the same. At all points on the surface. So what that means is when we look at this integral, maybe some of you can figure out what we can do with it. What can we do to simplify this integral if this is true, if the electric field's the same at every single point on the surface?
You can simply pull out the E since it's constant.
Yeah, E is constant, so we can pull it out, right? And now we just have that. And anytime you have an integral like this, like let me give you some simple examples that will be really easy to figure out. What's the integral of dx equal to? It's equal to x plus some constant, right? So if I have something like this, I'm just going to get a, right? And it says to do the integral, this circle again, it means that we're going to evaluate our integral over the entire surface. What that ultimately means is we're doing effectively like an infinite sum, right? We're coming to every single little point on our surface here. We're looking at the value of the electric field and we're dot producting it with the size of our little area that we cut out of here. Now the size of the area that we cut out of here, it could be a meter squared, it could be a millimeter squared, it could be anything we want, right? But imagine that it's just a quantity of some area, right? So you're coming along this entire surface and you're saying, let's cut it up into 1 millimeter squared blocks, so little tiny blocks, right? 1 millimeter by 1 millimeter. We cut the entire surface like that, and then we take the value of the electric field, which we know to be the same at every point on the surface, like maybe it's 10 or something, right? So we would say that right here you get 10 times 1 millimeter squared, right? And you come over here and you get 10 times 1 millimeter squared, right? And then you do that sum across the entire surface, keeping in mind that all of them have the same electric field. So really you're just going to take 1 millimeter squared plus 1 millimeter squared, and you're just going to add them up over and over and over again until you add up every single piece that you've broken your surface up into, which means that when you do this integral, all it's going to give you is the total surface area of your object. This is going to end up giving you the surface area of the sphere. Does that make sense?
Mm-hmm.
So we're going to end up getting the size of the electric field, which we know, and I'll plug that in a second, multiplied by the surface area of the sphere. That's really all that that says to do. So let's solve this now. So we have flux is equal to electric field. Electric field is this, right? It's K times Q divided by R squared, but we don't have a vector sign on it anymore because we took the vector sign out at the very beginning when we did the dot product. We did the dot product, we pulled it out, it's just KQ over R squared now, right? We have to multiply that times the surface area of a sphere. The surface area of a sphere, what is the surface area of a sphere?
4 pi r squared.
Mm-hmm. Yep. So look what happens.
Hallelujah.
You've eliminated the radius. And all we have left over is 4 pi times k, all of which is a constant that we're going to rewrite, multiplied by the charge that's inside the cube, or inside your sphere. Right? But what's 4 pi k equal to? Does anyone remember?
1 over epsilon naught.
Exactly. 1 over epsilon naught. So this whole thing leads to the fact that our flux is equal to the charge divided by epsilon naught. And that's actually what Gauss's law is. We basically just derived Gauss's law in a way. It turns out that the flux is equal to the charge that's inside divided by epsilon naught. That's it. This is basically Gauss's law. We're going to write it in a different way, and I'm going to talk about, like, we'll think about what happens if you double the charge. We'll think about what happens if you double the size of the sphere, all that kind of stuff. But that's what you get as your answer. It looks like the flux is, what is it independent of? Most importantly here. The flux is independent of what?
The radius.
The radius, yeah. The radius did not matter, right? The radius doesn't matter. Okay, so we'll take a break right there. And I think I'll put another problem up on screen for you to look at while we're on break. And yeah, we'll keep going. So let's take a break for 10 minutes until 3:13. And I'll stop recording.